floor is yours.
Thank you. Let me start by thanking the organizers for giving me this opportunity to speak here. So, as you see, I'm going to talk about hierarchical topology. I'll define what hierarchical topology is, and then in the context of synthetic flat bands, particularly the synthetic flat bands is hosted in this Josephson junction. This work is done in collaboration with two of my ex-students. Shubhadev is in Taipei doing his postdoc in Institute of Physics, and then Abir is in Weizmann Institute, and Udit is in PRL presently, maybe here somewhere. Okay, so we cannot start the story. So this is the story of Josephson junctions, and probably you should not be starting the story without thanking the three or acknowledging the three Nobel laureates, the supervisor, the student, and his postdoc, right? So it's a fantastic team. Very nice to see that, three people who are from the same lab got the Nobel Prize. And their Nobel Prize work essentially alludes to this fact that you could see quantum physics at human scales, to be more specific, to see quantum physics at a circuit scale where you have electronic circuits which you can hold in hand. So, and this essentially give rise to the whole physics of, the superconducting qubits and so on. And the motivation, as you can see, the Clark himself kind of says that he was motivated by Brian Josephson's work, and this is the story about Josephson junctions. So I'm going to straight go into Josephson junctions, the definition of Josephson junctions. So in simple words, if you have two superconductors which are separated by a thin layer of insulator, we know that if you drive a current through an insulator, it has a finite resistance, so it should have a dissipation of I squared R. But it was surprising to see that if you sandwich it between superconductors and put a phase bias, superconducting phase bias across the junction, then you get a current which is non-dissipative, which is saying that I squared R is 0 up to a critical current, and that was Josephson effect. It was a spontaneous ground state current in some sense. So that is given by this relation where you see that when the phase bias is 0, your current is 0 and otherwise it's finite. And also if you put a bias across the Josephson junction, then you start driving this phase. It becomes a function of time. It's more like a Floquet problem in principle, and you start getting this kind of a relation between the rate of change of flux and the applied voltage, where phi naught is the flux quantum. So these are the two things which I'm going to focus on. The DC Josephson effect, which is governed by this equation, and the AC Josephson effect, which is governed by the second equation. So this is the setup which you're going to work with. So you can see that this is the three-terminal setup. You have three Josephson junctions. So this is a superconductor, this is another superconductor, this is another superconductor, and there's a junction in between. There are two relevant fluxes here, one flux driving these two junctions, and the second flux kind of driving these two superconductors. So you can think of it this way, that this could be a platform for hosting a synthetic band in the following sense, that whatever spectrum you have for this junction, that should be periodic in phi, and we have two such parameters, phi 1 and phi 2, the first flux and the second flux. And we also know that in the junction region, if you have a piece of metal, then essentially there are electrons and holes, and in principle these electrons and holes slosh back and forth to give rise to coherent bound states, and these bound states are functions of this phi 1 and phi 2. So you can think of these bound states hosted right at the junction as in terms of some kind of a pseudo band or a synthetic band, where the crystal momentums are given by this phi 1 and phi 2 because these are compact variables. Okay, so that's the idea. That's the idea of having some kind of a synthetic platform for band structure. And then the question we are going to ask is that, is the interesting topological properties of these bands, and how does the interesting topologies of these bands influence the AC Josephson effect and the DC Josephson effect? That's the question we are going to ask. So these are the references. So this is where the story starts, and then there's a lot of paper, there's a lot of interest, particularly Julia Meyer has been very interested in this topic, and she has been producing a lot of interesting work. But what the community seemed to miss is, this is what we are going to point out, is the fact that when you're looking at the Josephson effect, mostly we focus on the Andreev bound states, and actually the continuum is supposed to be inert. But that's really not the case. If you pay attention, you will see that there's a specific case, which I'm going to tell you about, where there is a topological contribution coming from not from the Andreev bound state, where the Andreev bound states are actually inert, while the topological contribution is actually coming from the continuum. And that's exactly the focus of my talk. So this is the first part. So we'll talk about some anomalous Chern topology and quantized dipole. So I think thanks to the previous speaker who talked about dipole, quantized dipole, we'll also talk about that. So this is the band structure. So you can parameterize the junction in terms of a certain minimal parameter required to parameterize the junction, and then you see that you get all this beautiful band structure in the junction. Now you note that when you see topological transition, essentially you talk about gap closing because the topology is protected by the gap in the spectrum, and the gap closing can be of two types once you are in superconductor, because now you have this enrave states which are inside the gap, and then you have the whole continuum outside. So the way to close the gap, so you have this enrave bound states which can touch each other. In the first case, you can see that there's a gap closing here, where as a function of flux, the enrave bound states go and touch each other in the momentum space. But on the other hand, you can also have a gap closing where actually the enrave bound state go and touch the continuum. So of course, there is a continuum above and below, and there's a gap in between, and the continuum are connected by the particle hole symmetry. So if they are connected by the particle hole symmetry, once the band goes and touches the continuum on two sides, actually it's like closing the gap by particle hole symmetry. So there are two ways you can close the gap. One way is to directly close the gap, another way is through the continuum. And what you see is that there is a whole class of gap closing and also some interesting stuff where there are flat bands in this band structure, and this is the focus of this talk. We know this is the standard expression for Berry curvature in these band structures, and this is the Chern numbers expression, which is nothing but a Gauss's law. It tells you how much charge is inside the closed surface. So this is what you observe. So in this, if you look at the Chern number of this band, what you see is that in the parameter space, which is a one-dimensional minimalistic parameter space, what you see is you start with a Chern number +1. At some point, the Chern number goes to 0. It's like a topological phase transition. Then it is 0 all through, and then suddenly switches sign and then get quantized again, and that is what we see. What is interesting here, or what is anomalous here, is the fact that whenever there is a gap closing, we expect Chern numbers to change or some topological transition to happen. This is what is happening in the first band closing. But then once the Chern number is 0, we also have another band closing where nothing happens, as if there is something anomalous, and it continues to be 0 all the way till here, right? And then there is a Chern number change. So the first question we asked is that, why is this anomalous feature appearing? What's going on here? So to understand that, the one way to do this is to really see, when you are looking at Chern numbers, the Chern number can be associated with a monopole charge, and you can ask this question that you are in the Brillouin zone. It's a two-dimensional Brillouin zone. So basically you are on a torus, and you can ask this question, is this torus encapsulating your monopole, or it's not encapsulating your monopole? If it is inside, if the monopole is inside the torus, you get a quantized charge, which is your topological quantum number, which is +1 and -1, depending on the sign of the charge, or else it is 0. Now you see that what is happening in the anomalous point is, initially it is inside when it's +1, but at some point you gap close, it changes at this point, but then it stays 0, but that doesn't mean nothing is happening. Actually what is happening is, the monopole goes out, and at some point it starts coming back and just comes and touches the surface and bounces back, okay? So that's the anomalous point. At some point you have some anomalous gap closing, but no Chern number changing, where what is happening, at least from the perspective of enrave bands, what is happening is the monopole is outside, it comes, touches the surface of the torus, and then bounces back. And then at some point it changes sign and goes inside. So that is how you come from -1. So you start from -1, remains 0, but there's something interesting going on here where it touches and then goes off. Now, this is interesting, but it still doesn't tell you what's going on. What is the physics that's going on? When it's touching, what is it exactly changing? So if you pay attention to essentially, now once the Chern number is 0, it's telling you that the integrated Berry curvature is 0. There is no net magnetic field in the Brillouin zone, but there is a distribution of magnetic field in the Brillouin zone, and you need to pay attention to that. As you start paying attention to that, what you see is that, so before this gap closing happened and after this black gap closing happened, the places where, so the total magnetic field is adding up to 0, magnetic flux, but there are centers of positive magnetic flux and there are centers of negative magnetic flux, and across this gap closing point, essentially when the monopole comes and touches it, they switch sign. So there is something interesting going on, but not really in the Chern number, but you have to go higher. So the natural thing is that there is a charge distribution, which is just switching sign. So the thing which comes to your mind naturally is that you must look at the dipole moment, right? The next hierarchical object. So that's exactly what you look at, and what it turns out is that if you see that this is the P2 is the dipole moment, and you can see that P2 is 0 initially. Sorry, and then it gets quantized. Then at the gap closing point, it and then again collapses to 0, again goes up, gets quantized, and then goes down. So at the first transition point, when the Chern number goes to 0, actually what happens is that this higher order object, which is the dipole moment of the Brillouin zone, that becomes quantized. And exactly at the middle point where there is a gap closing, all quantum numbers, we even checked quadrupole moments, all higher order topological invariants, they all go to 0. Okay? So that's the physics which is going on. And we need to understand this physics from the perspective of these currents which you can measure, which is the DC and AC Josephson currents. So now let's focus on the next interesting topic, which is completely flat band, flat and reef bands. So this is not a new topic. I mean, this is of great importance as far as the standard, superconducting qubits are concerned. They can be topological in principle also, but let's say that you are looking at the, superconducting qubits, and ideally what you want is that these superconducting qubits better be stable, which basically means they should be immune to flux fluctuation and charge fluctuation. Now, if you are in the Coulomb blockade regime, then you expect that the charge is a good quantum number. The question is, can you control the flux? Because if the flux is fluctuating, there's not a good qubit. Now, if you have a flat band in the phi 1, phi 2 plane, it's essentially saying that the energy levels, the Andreev energy levels, are insensitive to the changes of flux. That's exactly what you want. So this is a patent which essentially talks about a sweet spot, in the sense that in the phi 1, phi 2 plane, can you find a spot which is a minima or a maxima so that you have some first order stability of the flux fluctuation. What we have found here is something much better than that. We have a flat band. You can fluctuate the flux as you wish. If you fine-tune your scattering matrix parameter in the junction to this point, you just have no sensitivity to flux. So if you encode some quantum information and finally fine-tune here, then the point is, it's going to stay there, right? Because flux fluctuation is totally irrelevant. So how do you do this? So this is a simple-minded junction. You have superconductor 1, superconductor 2, superconductor 3, and then there is a junction in between, which you can think of as a piece of metal, and this is the circuit, this is the driving flux, and this is the grounded terminal where you can put a voltage V3. Now, if you look at the current in this terminal, the terminal currents looks like this. That ignore this factor, it's just some distribution function stuff, which you can ignore for the moment. The interesting physics is here. This is the DC component, DC contribution to the current, which comes from dE d phi. Those who deal with Josephson junction, you all know that the current, the DC Josephson current, is coming from dE d phi. Now, E is the energy of the flat bands, okay, of this Andreev bands. And if they are flat, it's telling you that they have no dispersion in the momentum space, right? That basically means dE d phi is 0. So you have no DC. Once you have a flat band, you have no DC Josephson effect. Now let's look at the AC contribution. The AC contribution actually depends on something which is the Berry curvature. And if you integrate over the full band, then you see that this will be proportional to something which is a Chern number. So if your Chern number happens to be 0, which basically means if your flat band happens to be something which is topologically inert, which is like the Chern number is 0, then even this contribution is going to be 0. So the current response of this entire junction in the flat band limit, be it AC, be it DC, is absolutely 0, right? That's fantastic, because no fluctuation is going to, neither voltage fluctuation nor flux fluctuation can actually disturb your information. But is this the full story? That's the question. So what I have done here is, of course, I'm telling you a story which is focusing on just the Andreev levels, and I'm not focusing on the continuum. Question is this correct? This is what the community does, but is this correct? This is just a reiteration of the same fact. So I'm not going to say you get 0 current here. Let's move ahead. Yeah. So now you need to pay attention. The fact is, when you look at the current is coming, the total current contribution actually comes from all the filled band below, okay? So you have this gap, and you have some Andreev bound states here, and there's a continuum above, and there is continuum below, and the Fermi level is somewhere here. So you need to take contribution from all the bands, be it the Andreev bands, be it the Bogoliubov continuum, right? You can't ignore anything. In principle, in most of the cases, the Bogoliubov continuum does not contribute. So it doesn't matter if you throw it away. But in this case, we need to pay attention. So the dE d phi should get contribution from the Andreev bound state, but we should also pay attention to what is the contribution coming from the continuum. Similarly, the Berry curvature, we should not just calculate the Berry curvature of the Andreev bands, we should also calculate the Berry curvature of all the Bogoliubov bands, or all the Bogoliubov states there above and below, okay? And then we'll have a clear picture, but this is analytically hard, so you're going to do a numerics for that. And particularly in presence of a finite bias, you know that the flux has become a function of time, and it becomes a complicated Floquet problem. So doing it by hand just gets tricky, and you need to do a numerics. So if you do numerics, what you see is the first thing we do is, as a function of flux, we try to see in the flat band limit what is the kind of density of states variation you see as a function of flux. You can see that in the flat band limit, this is the flat band limit, the density of states is absolutely flat. It has not just the Andreev bound state, the entire Bogoliubov continuum does not respond in the flat band limit to the fluxes, no matter what the flux value is, right? The density of states is just flat. So at least it tells you that this first contribution, the DC Josephson effect, is indeed 0 no matter you look at the continuum or the Andreev bound state. Now let's look at the next contribution, which is coming from the Berry curvature. So what you observe is the following. This is what our numerics gives us. So the numerics gives us the total Chern number. The total Chern number of the band, which includes the Andreev band and the continuum, is actually 0 to begin with, which was looking quantized when I looked just at the Andreev band. Okay? So it's telling you that the Andreev bound state and the continuum actually share exactly opposite Chern number, and the total Chern number is 0. So there you get 0 response. There is no response. The current is 0. The DC Josephson current coming from both contributions actually cancel out to give you 0. No currents. On the other hand, once you go to this dipolar phase, there is actually a net Chern number. You remember the Chern number from the Andreev bands were 0, but this is completely coming from the continuum. So now you see there is something very interesting. The continuum in this case is playing an extremely important role. The Bogoliubov continuum is actually having a quantized response, right? It's behaving like a Chern insulator, while the Andreev bound states are totally inert. And then you have a phase transition here. That was the anomalous point. Anomalous from the perspective of Andreev bound state, but once you take the full spectrum on board, there's nothing anomalous about it. It's just very understandable. And then there's a phase transition. The Chern number changes sign, so does the conductance, and then it goes to 0 again. So that's the complete picture. And now this is the summary. This is the phase diagram. How am I doing in time? I think I'm doing well in time. So okay, fine, good. So what you see is, if you look at the total Chern number, so this is the parameter space. The total Chern number in the parameter space begins with 0. Then there's a patch of Chern number +1, then there's a patch of Chern number -1, and then Chern number 0. So that is the total Chern number, and this is how the conductance will go. So total conductance initially is 0, then it will be quantized to +1, -1, and 0 again. Now if you look at the ABS, the Andreev bound state Chern numbers, then the Chern number is -1 to begin with. Then there's a whole region of Chern number 0 with this anomalous point here, and then Chern number +1. Okay. Now the continuum Chern number is just opposite. So you see that here, initially in this patch, the Chern number is +1 for the continuum. It continues to be the +1 all the way to the center, and then it switches sign. There's a phase transition here, and the Chern number becomes -1. Now this is the classification from the monopole. Essentially the Chern number corresponds to a singularity, which is a monopole-like singularity. Now we look at the hierarchical object, which is the next in the hierarchy, which is the dipole moment, right? So what is the dipole moment doing? So you see that initially the dipole moment is 0. Then we have a region of quantized dipole moment. Then it's unquantized, and again quantized, and again the dipole moment is 0. So that's the full picture. And now in this picture, if you start looking for the chiral point, which I said where the flat bands are, the flat bands, you see the flat band point is here. So flat bands have a quantized dipole moment, have a Chern number of +1 from continuum, Chern number 0 from the Andreev bound state, and the net Chern number is +1. Okay? So these are the two chiral points. So that's pretty much the summary. Any question till this point? Because I think I'm doing pretty well in time, yeah? I have 5 minutes. I don't need 5 minutes, I think. Okay, I'm pretty much done. So what is the summary? The summary is the following. So if you look at the Andreev bound states, so these are the Andreev bound states inside the gap. This is the continuum above, this is the continuum below in both cases. So you have, in principle, when you verify, the Andreev bound state actually go back and forth while the continuum remains almost inert. We have a case where essentially these are flat bands where the Andreev bound state does not respond to the phi at all. That's one of the things very important for us, because as I said, if you want to prepare a Andreev qubit, Andreev bound state based qubit, which is very popular these days, most of the companies are doing that, then you better have a situation where you are insensitive to the external flux and its fluctuation. Right? So we have got that. That's the flat band limit. And in this flat band limit, if you look at the net DC Josephson current as a function of phi2, it typically looks like that for a normal junction, but in our case it's identically 0. Okay? So there is no DC response. Now if you look at the AC response, in general, it kind of shows some kind of periodic behavior, but for us, it's a quantized response, AC response. And this quantized AC response typically comes from the Andreev bound state, but for us, it's not from the Andreev bound state, it's coming from the continuum. Okay? So that's the message. So that's my summary, and I think that's it. Thank you.
Thank you for finishing on time. So we have time for questions.
Thanks, Shooting. Wonderful talk, very stimulating. I have two questions. One
Please.
maybe is slightly just my brain freezing on me. And yeah, so when I think of what you called a very curvature dipole, and I think of say something plain vanilla like hexagonal boron nitride, where you have very curvature plus on one valley and very curvature minus on the other valley. So
What's going on for us?
what's going on? Why,
Okay, I'll tell you.
Would you call that a topological phase of matter because it has a very curvature dipole?
It's a quantized Berry curvature dipole. It's not just a Berry curvature dipole. We have a regime where it's completely quantized.
And what is protecting that quantization?
Very hard. I don't understand it. Honestly, I don't understand it. To be fair, I'll tell you. So, see, I'm completely working in the momentum space because the phase bias of the superconductor is acting like a quasi-momenta, right? And I have two of them. So now you can insist that now that you know the dispersion in the momentum space, why don't you Fourier transform it back in two dimension, assuming let's say square lattice, and then what do you see? I can assume any lattice I like. I don't have a prescription because let's say I take a square lattice, I go back, and what you see is that mostly you get a lot of non-local hopping. So it's not a standard nice local hopping picture which you get as you go back to the momentum space. So it's very hard for me to go back and kind of do an analysis which is standard. As you said, plain vanilla analysis is not possible. But we have been trying this to find a lattice in which it will look local. And as of now, I don't know.
If I did this just for HBR and I found a limit in which I got
that will be
plus
nice.
And minus, then you would say that is a quantized very curvature.
I have to calculate it and see that it's really, it's very hard to say. In our case, it really turns out to be quantized. What is happening is exactly, it's like you are getting a patch of the Brillouin zone where you have a Chern number +1. You have another patch where it's Chern number -1. They sum up to 0, and they switch as you go through the transition. This is what you observe. Now, what it means for the lattice, because it's a synthetic platform, is very hard for me to say. We are trying to find a nice lattice where I can have a nice interpretation for it, but it's completely open. The system does not impose a lattice on me. I don't know.
Whenever we actually study about any Chern number, so non-zero Chern number, it's related to something like if you look in a region system. So if suppose let's take 1D lattice, so we generally get
1D you won't have it.
So
you need at least 2D.
For example, binding number, something like that. So like maybe we have the edge states or surface states. So what's actually here the topological meaning? Like if you want to look at in something.
See, edge state is a manifestation of the topology. It's not that you have to have edge state. So the point is, if you cut it open, if you cut your system open, you're going to have edge state. But if you have just a periodic boundary condition, there are no edge states. But that doesn't mean that it's not topological. You have magnetoelectric response, which will get quantized. So you don't need to look at different other responses, which does not require the system to be cut open, right?
Okay, so one more question. So this dipole moment is higher order actually topological property or actually. So I saw there is some so like you are scanning some parameters or I think.
It's the parameter which corresponds to the engineering of the junction. What kind of a junction you have and what kind of resistance network it corresponds to.
So I saw in some region there was not contact. There was something like it was going down.
Yeah, so there was a region.
Topology in that sense.
I don't know. I don't know. What I know is that, and that is the point where all my topological quantum numbers are 0. My Chern number is 0, my dipole moment is 0. We also calculated quadrupole moment that turns out to be 0. It's one of the trivial points where all the topological invariance collapses. That's an observation. Why? Exactly, I don't know.
So this discussion can be over. So I don't need the mic. So how much of this is dependent on fine tuning? Because you have a unitary matrix, 3 by 3. It has 9 parameters.
I see. No, I think I think I'll tell you, give you the same answer which I gave you a few months back. Is the same sense that as long as you are in the vicinity, I won't say you are exactly there. You are in the reasonable vicinity of absolutely reciprocity. If you break reciprocity to its maximum limit, which means that transmission from 1 to 2 and 2 to 1 are absolutely skewed, which is like extremal breaking of time reversal symmetry, and a reasonable neighborhood of it, you remain reasonably quantized. All the answers pretty much go well. And the window over which this happens is not very small, so I won't say it's that fine-tuned. Many of the topological quantum numbers remain pretty decent in its neighborhood.
So this is 8-dimensional neighborhood at this point.
Yes, and the blob is quite kind of robust. Yeah, naturally. Yeah, there are no very fragile directions in which you can run off and get complete breaking of this topological protection. No, at least our numerical analysis do not show that.
Yeah, we are short on it. We can take one pressing question and then. Yeah.
Thanks for the very nice talk. I think I did very well, I guess. So, if you go back to your phase diagram, at some point you showed that you have a quantized dipole moment as well as a Chern number which is a monopole invariant. So, typically the way we understand the development of higher order topology is that if you look at the nth moment and when it is quantized, it better be invariant under coordinate transformation. So that implies that all the lower order moments must vanish.
See here, very good point. See here, so why I say it's a higher order topology, we have a very weird situation. You have different parts of the system having different topological invariants. So the enrave bands are the subgap bands. The subgap bands have a topological number associated with it, which is the quantized dipole moment, but the Chern number is 0. On the other hand, the continuum shows a quantized Chern number. Of course, Chern number is quantized, but no dipole moment. So different parts of the spectrum kind of shows different topology, and that's what is very exotic, Yeah.
Yeah, thank you.
I think I should stop now, right?
Thanks for this talk. And